Okay, just let me revise what I thought in the morning quickly so that this is what I was discussing about the downlink transport channel processing. I said that it has two parts. One is channel coding processing and one is modulation processing. So in the morning class, I discussed about this channel coding processing. Okay, so I told about CRC addition, code block segmentation, channel coding, rate matching, and as well as code block concatenation, right? So what is happening here? Uh, the information from the higher layers, right? That is output of MAC layer will be in the form of transport blocks. So that depends on the size of the transport block. I said it depends on the type of coding scheme used and as well as the type of modulation scheme we use. Then for that transport block, the CRC bits will be added. So the purpose of CRC bits is what? To detect the errors. I said usually 24 bits of CRC will be added here. Then the transport block with CRC, okay, will be of larger size. Okay, so that will be segmented in the code block segmentation. Okay, so transport block with CRC will be again split into sub blocks along with the CRC. That is what is happening in the code block segmentation. Then output of the code block segmentation is done what? Channel coding, right? Means each block of the code block segmentation, let us, if I consider a 1 bit, then depending upon the channel coding type, right, with a coding rate of 1 by 3, means for every 1 bit I will be getting 3 outputs, 3 bits as output, right? So like that I told in terms of blocks only, how many, for 1 row I will be getting 3 rows as output in the channel coding. Then the rate matching, what it will do, it will convert the output of the channel coding, right, which is having for 1 bit 3 rows, right? So this will be converting back to R rows, okay, right, from 3 rows to R rows. That is here the 3 by R row will be there, output of the channel coding. So this, then output of this will be rate matching is given as input of our code blocks concatenation. Now here what is doing in code block concatenation, from different sub blocks, right, with interleaving, it will be made as a single sequence. So that is what I discussed in the morning. Okay, just let me show with the diagram. I think, yeah, this is what the entire process, what is happening in the channel coding processing. I said transport block, then CRC will be added to this transport block. After that, this transport block with CRC will be again segmented into C blocks. Okay, that is why it is written code block 1 with CRC, code block 2 with CRC, and so on up to code block 3 with CRC. Right? I told with when do we do this segmentation? After doing segmentation, we do the channel coding, right? So depending upon the type of channel coding and coding rate, for every code block, I get means if I use a coding rate of 1 by 3, so for one code block I will be getting 3 code blocks. Okay. Then the rate matching will be done. Okay. Then what I said, code block concatenation is done. Just I will show the diagram so that yeah, I think this is what the transport block information bits, then CRC bits added here, right? So this I said A is the transport block information. After adding CRC bits of 24, I say that as B. So B is equal to A plus 24. Then, yeah, after that, this B is equal to A plus 24, right, is of a big size that will be divided into sub blocks, right? That is what is known as code block segmentation. So which is done here. Okay, for every segmented code block, the CRC will be attached. Okay, so that is what is shown. Then, yeah, depending upon this type of coding and coding rate, as I said here, for every one row, means what I said here is given to sub segment blocks. No? For every row, there will be three output rows. That depends upon the channel coding type. So this is my output of the code segmentation block, right? For every row, there will be another three rows. For one row, I will be getting three rows as output at the output of the channel coding. That is why it is written 3 by R rows. Okay. Then after channel coding, the rate matching will be done. So the rate matching uh, is what the rate matching consists of these three steps: interleaving, bit collection, and as well as bit selection. So what is done in interleaving, bit selection, and bit collection? So means for one block I get three blocks, right? Output of the channel coding. So that 3 by R rows will be converted back to R rows, okay, with the rate matching. That's what I wanted to say here. Okay. So here I'm getting R rows, right? That is output of the rate matching. By doing what? By doing interleaving, bit collection and bit selection process. So that is what I think, yeah, here it is. This is what the rate matching operation. So code block will have systematic stream and as well as a parity stream. So sub block interleaver will be there, then bit collection is done, then bit selection. So in simple words, what I can say, this is what the rate matching operation, right? Output of the encoder, channel encoder is passed through a sub block interleaver, then bit collection will be done, then bit selection will be done. So with that, what I said, I will be getting from 3 by R rows to R rows, right? Now, output of this code block concatenation, what I get, a single stream of data. Okay, here I will be getting R rows of data, right? That will be converted back to single row of data. So this is what is happening in the channel coding process. So with this, let me take the next thing, that is the modulation processing. Okay. Yeah, I hope it is visible now. Modulation processing. So these are the different steps involved in modulation processing, right? See, output of the channel coding process, that is output of the code block segmentation, will be given as input to this here, right? So we get the code words, right? So those code words will be applied to the scramblers. So the scrambling of the coded bits in each of the code word to be transmitted on the physical channel. Okay. Then out of the scrambling will be given to the modulation mapper. Okay. So this modulation mapper, what it will do is it will do the modulation of the scrambled bits to generate the complex valued modulation symbols. Then it is given to the layer mapper. Okay, what this layer mapper will do is it will map the complex valued modulation symbols onto one or several transmission layers. That is why I'm getting here layer mapper, layer circuit. Then pre-coding is done. So pre-coding of the complex valued modulation symbols on each layer for the transmission of the antenna ports. Then the resource mapping will be there. So this will map the complex valued modulation symbol for each antenna port to the resource element. Hope you understand the meaning, what is resource element and resource block, right? Then from that, we know every resource element is corresponds to one OFDM symbol and one subcarrier frequency. So with that, I will be able to generate the OFDM signal. Okay. So this is how happens in the modulation processing. I think, yeah. So I told here in simple manner. I think with expressions, if at all you want to understand, this is what the explanation is. So with respect to the first step, that is the scrambling, right? So what happens here? The code word generated through the channel coding processing is first scrambled by bit level scrambling sequence. So that bit level scrambling sequence is denoted like this. The block of bits for code word Q is denoted by like this. Okay, where m suffix b of q is the number of bits transmitted in one subframe. Okay, one subframe will have again what, two slots. So one slot will be having 7 OFDM symbols. So two slots, that is 14 OFDM symbols, right? So the scrambling sequence is basically a pseudo-random sequence, uh, which is of length 31. You all have studied in digital communication about that. That is a gold sequence. Hope you will be able to recall and get back that. So that is what is done in the scrambling. Okay, so the scrambled bits are generated using modulo 2 addition, what we say. So this is what the expression for that. Yeah, so up to two code words can be transmitted in the same subframe. Okay, so this will be the length of the code word. So two code words we can transmit over the one subframe. And the value of this q here. So b power q of I is equal to b power q of I plus c power q of I mod 2. So the value of q will be 0 if the spatial multiplexing is not used. And if spatial multiplexing is used, then the value of q will be these two values, 0, 1 it will take. Okay. So scrambling sequences are different for neighboring cells. Hope you get that point. That is, intercell interference will be randomized for all the downlink transport channels and control information. Yes, for multicast channel, the common scrambling is applied for all the cells involved in the specific MBSFN transmission. So MBSFN means multicast broadcast single frequency network. It is okay. Yeah. Then output of the scrambler, right, is given to the modulation mapping asset or modulation mapper. So here, what is happening here is for each code word that we get Q block, right? So the block of scrambled bits are modulated into block of complex value modulation symbols. So this is the code word BQ of 0 to B of this one that will be modulated. The modulated bits will be denoted by DQ of 0 to D power Q of this. Okay, so this M suffix S to the power of Q indicates the number of modulation symbols in each code word, and that depends on the type of modulation scheme. Means if I use QPSK, the value of this will be 2 bits. If I use 16 QAM, then the value of code words will be 4, right? Like that. And this is what the relationship between ms to the power of q to the mb to the power of q. That is the number of block uh, of scrambled codes to number of symbols in the modulation. Okay. So ms to the power of q is a what? I said number of modulation symbols in each code word, which is equal to mb to the power of q. So mb to the power of q is the block of scrambled bits, right? That divided by q suffix m, where q suffix m is the number of bits in the modulation constellation. Yeah, so this is what the table which shows different modulation schemes with the different channels, physical channels. Okay, if the physical channel is PDSCH, that is physical downlink shared channel, and these are the modulation schemes supported. So QPSK 16 QAM and 64 QAM. And if it is PMCH, then these are the modulation schemes supported. So if it is PBCH or PCFACH and PDCCH, the type of modulation scheme supported is QPSK. Okay, for PHICH, the BPSK is used. Yeah. So after modulation mapping, that is output of the scrambler modulation mapper I said, na, then there will be layer mapping and pre-coding, right? So in layer mapping, what happens? So the code words, okay, uh, here these two steps map the incoming code words to up to 4 antennas. Okay, means so the layer mapper will map n suffix c code words to v spatial layers. Means n suffix c can take the value of 1 or 2. So there is a code words. So the v layers, this v number of v layers will be greater than or equal to number of code words. Then the precoder will map these v layers to p antenna ports. Okay, here antenna ports are different and number of antennas are different. Okay, so yeah, I think yes, what I said, code word is defined as the what output of each channel coding, right? With a single transport block coming from the MAC layer. So in LTE, I said the number of code words is limited to 2. Right? So this is to limit the uplink feedback overhead. So a separate hybrid ARQ process is operated for each code word, so which requires separate signaling in the uplink control channel. So layer corresponds to the data stream of the spatial multiplexing channel. That is why layer mapping. Okay, so each code word is mapped into one or multiple layers. Then antenna port, what I said, antenna is different, antenna port is different. So antenna port is defined by its associated reference signal. Okay, and it is a logical entity, may not correspond to an actual physical antenna. Okay, so the number of transmit antenna ports at E node B is sent to the user equipment through this channel, PBCH channel, which can be either 1, 2, or 4. Okay, in the LTE. Okay. Yeah, so I was talking about this antenna ports. No, I said antenna port is associated with the reference signal. Okay, basically it is a logical entity and it will not corresponds to the actual physical antenna. I said, right? So the number of antenna transmit antenna ports at the E node B will be sent to the user equipments through this channel, PBCH channel. Okay, so it that can be either 1, 2, or 4 in LTE. And these antenna ports are divided into 3 groups, what we say, that is antenna ports 0 to 3 are cell specific, so which are used for downlink MIMO transmissions. And antenna port 4 is used for MBSFN, right? So So antenna port 4 is specific for MBSFN and is used for MBSFN transmission. And antenna port 5 is user equipment specific. Okay, so hope you are able to grasp this. What is cell specific, what is MBSFN specific, and what is user equipment specific. So if you are able to take that, that will be more than enough, what I feel. So antenna ports 0 to 3, I said they are for cell specific, which are used for the downlink MIMO transmission. And antenna port 4 is MBSFN, I said, which is used for MBSFN transmission. And antenna port 5 is user equipment specific, which is used for beam forming to a single user equipment using all physical antennas. So 0 to 3 means here 4 will be there, this is 5 and 6. Totally 6 antenna ports are there. So this is about the what layered architecture, right? That is layer and precoding. Then I think just get an idea how that precoding is done in case of MIMO. Okay, so all these things are not as per your text, but it is there in other modules. Okay, so to get an idea, I'm just showing these diagrams. So precoding, how it is done, what is the distance between these two antennas, which is of lambda by 2, and this is signal 1 and signal 2, right? How do we get that one? Okay, by adding that. Yeah, I will skip this. This is all required for precoding. Okay, so this is the code index and number of layers it is. What is the V, what I used to say. Okay. Yeah, I think I can skip this open loop and closed loop MIMO also. Yeah. Yeah, to get some idea, just see this is what the code word is, right? And how does it gets transmitted to the user equipment. See, this code word is sent redundantly over several streams, right? So this is over the PDCCS indication via DCI format 1 or 1A. So many things are there to understand. I will just, okay, I will skip all these things just to get an idea. I was telling, no, cell specific and user equipment specific ports cannot be simultaneously used. So these are the antenna ports, which are there in ENB. That is there at antenna node, E node B, right? That is port 0, port 1, port 2, 3. So port 5 I said is used for beam forming. Port 0, single antenna transmission, right? So 0 and 1 used for two antenna transmit diversity and spatial multiplexing. Then 0 to 3, right? That is for 4 antenna transmit diversity and spatial multiplexing. Yeah, this is about the further understanding about precoding. I will skip that. Yes, this is what we do the conversion of code word to layer mapping for spatial multiplexing. So there are the number of layers. Okay, if it is 1, code word will be 0. That is a layer 0 we say. Then number of layers is 2. Then we say layer is 0. Code word is layer 1. Like that. Okay. Yeah, I skip this also. Yes, of course, this table indicates about the supported MIMO modes for different physical channels. Okay, with respect to single antenna port is what? Open loop and spatial multiplexing. Just have a look. Yeah, this is about the resource mapping. That is output of precoding will be going to the resource map, right? How does it map to the resource element? So that is what is done here. Then I think I don't know. See, for each of the antenna port used for transmission of physical channel, the block of complex guard symbols are shown here. That is denoted as YP of 0 to YP of M suffix S to the power of AP. Antenna port AP stands for that -1. So that can be mapped in sequence starting with YP of 0 to resource blocks assigned for transmission. So the mapping to resource elements. So K comma L is the way we used to represent or indicate the resource element. An antenna port P not reserved for other purposes shall be in the increasing order of first and index K and then index I. Okay, starting with the first slot in the subframe. Fine. So yeah, I was talking about this when the FFT size is of 2048 and if the subcarrier spacing is 15 kilohertz. Okay, and when the subcarrier spacing is 7.5 kilohertz, we say the FFT size will be 4096. Obviously, it will be double than the previous one. And yeah, about the configuration, I was telling about normal CP and extended CP. In case of normal CP with subcarrier spacing 15 kilohertz, this is what the CP length, that is what cyclic prefix length. Okay. So what I mean to say is for normal CP, during subcarrier spacing of 15 kilohertz, the cyclic prefix length is 160. Okay, for L is equal to 0. And it will be 144 for these values of L. That is when L is 1, 2, up to 6. Okay. So L is what? That is the OFDM symbol. Okay, when 0 symbol, for that the CP length is 160. For further OFDM symbols, that is from 1 to 6, the cyclic prefix length will be 144. Okay, similarly for extended CP, this is what the length of cyclic prefix. That is 512 for L is equal to 0 to 5 and 1024 for L equal to 0, 1, 2. Yes, this is what the block diagram of OFDM signal generation with N users in the downlink, right? So N user data will be given to the resource mapping, so which is in frequency domain. Then that will be applied to IFFT. So this IFFT will convert this frequency domain signal into time domain signal. Then we add cyclic prefix. So parallel to serial conversion is done to get the OFDM signals. So this is in brief about the OFDM signal generation with N users. So it starts from resource mapping. Okay, so hope you'll be able to catch up this idea, because many times we say with different blocks, but you should be able to say what block to say at what point of time. Okay. Yeah, I think I will skip these things. What is MIMO and LTE? Okay, so that is single user MIMO, multi-user MIMO, like that, cooperative MIMO and all. Okay, so they're all there in your syllabus. Okay, don't think that it is all not there, but due to lack of time, I'm not touching these parts. So at least you should be able to know what is SISO, that is single input, single output. Then single input, multiple outputs means one transmit antenna, multiple receive antenna, that we call as SIMO. In case of single input, single output, one transmit antenna, one receive antenna will be there. Then in case of MISO, so multiple transmit antennas and only one receive antenna. So in case of MIMO, so multiple transmit antennas and then multiple receive antennas will be there. So at least you should have this idea in your mind. So four possibilities: single input, single output, single input, multiple output, then multiple input, single output, then multiple input and multiple output. Okay, so to understand MIMO, first we need to start with SISO, then SIMO, MISO, then MIMO. Okay. Yeah, I skip this. So also just yeah. Okay. Yeah, all it is with mathematics is there, pre-coding and all. That is, I'm not touching this. Yeah, spatial multiplexing also. Yeah. So I think with respect to the modulation processing, I think till this you can understand, till the OFDMA signal generation with n users. So how do we get the OFDMA signal? Okay, so this is what will end with your downlink transport channel processing, both channel coding and as well as modulation processing. So rest of the things what I add, that is all about MIMO, to make you understand about MIMO. So let me not touch with that now. So at least you should be able to cope up with this topic till this. So with this basic understanding about the downlink transport channel, so let me switch over to uplink transport channel. Okay. Yeah, this is your module 4, okay? Uplink transport channel processing. Why I covered the downlink is also part of your syllabus only. So now my job becomes easy if I can go fast with that. See, able to see the block diagram similarity and able to identify in what way this uplink transport channel processing is different from downlink transport channel processing. Yes, quickly, any one of you, is it possible to say? See, transport blocks, right? To begin with channel coding processing, every step is same. See, transport block, then CRC addition, code block segmentation, channel coding, rate matching, then code block code block concatenation. So all the steps are same. Then output of the code block concatenation will be in the form of code word, right? So we do scrambling, then modulation mapper, then DFT based pre-coding here. So this is what the difference is. DFT based pre-coding, then resource mapping, then this is another block where the difference is. That is SCFDMA signal generation. So instead of YFDMA, it will be SCFDMA. And instead of IFFT, it will be DFT here, pre-coding, DFT based pre-coding. So only this is the difference. So rest of the things are all same. Okay. So yes, you are all able to catch the point in what way the uplink transport channel processing is different. The signal generation is different. Okay, in case of modulation processing. So in case of channel coding processing, all the steps are similar. All the steps are same also. Okay, only in the modulation processing, two things are different. One is we use DFT based pre-coding. Then the type of signal generated is SCFDMA signal. Okay, for downlink it is OFDMA signal. So with that basic understanding of this, I will not spend much time again and again. So let me go to the next thing. Yeah, which I have highlighted in what way and which block is different, right? Yeah, just let me say what is the type of coding scheme preferred here, right? So for transport channel, that is an uplink. Uplink shared channel is there, right? And another one is random access channel. Okay, for this uplink shared channel, the type of coding scheme used is turbo coding with a coding rate of 1/3. Okay. So for control information, the channel coding scheme depends on type of control information. and also on type of physical channel that carries the control information. So the control information in the uplink can be mapped either to the physical uplink shared channel, that is a PUSCH, or the physical uplink shared channel, okay, that is PUCCH. Okay, and this is the usage of channel coding scheme and coding rate for the uplink control information, that is UCI. Okay, further block coding is used and coding rate is variable. And for another thing, it is tail biting conventional coding. Yeah, and this is how we say the SCFDMA signal generation. Okay, so the modulated symbols which we get from the output of the scrambler after doing the modulation mapping, right? So that is given to the DFT based pre-coding. Then resource mapping is done. So then IFFT, right? Output means here this is in time domain. It will be converted to, right? So frequency domain. Again, IFFT will, what it will do, it will convert the frequency domain signal into time domain signal. So then add a cyclic prefix, then do the parallel to serial conversion. We say that is what the SCFDMA signal is. So this is about the uplink transport channel processing. Okay, that is from channel coding processing to modulation processing. Okay, so the things are very similar. So that is why if you understand one thing properly, then you will get a confidence and to say what process is happening in the uplink. Okay, so just I will stop with this. Just let me share one small another tool where you will get just by googling, so that you will be able to do the understanding about the transport channel, what is the block size and other things. Okay, yeah, hope you are able to see my screen now. Yes, are you able to see this screen? There is a resource allocation type 2 downlink.
Yes, sir.
Yeah, this is just one of the company, it is okay. You will get that. That is ROHDE, Road Squads, I think, .com. Okay, just if you write LTE, resource allocation in LTE, so it is a resource allocation tool, it is actually, okay. So whatever I have discussed about this one, transport block size, already you can just check with that resource allocation in type 2, downlink, uplink and other thing. Just I wanted to show about the transport block size in downlink and as well as uplink. Okay. So just if you click on this transport block size downlink, see here, these are the uh, windows they made. So number of resource blocks, we need to enter the number of resource blocks. Okay, then the modulation scheme value. So it varies from 0 to 28. Means if it is 28, it will say what is the type of modulation you have selected. So it will be, since it is downlink, it will be we can use up to 64 QAM. Okay, and the number of antennas and as well as the number of PDCCS symbols. So either it will be one or two only. Okay, just I will show with the number of resource blocks. I can have 1, 10, 100 like that. Okay, so means even with the different bandwidths, you can say no. The number of resource blocks 6 also you can say, that is at 1.4 megahertz bandwidth. So I have selected number of resource blocks as 100, and I'm selecting the modulation scheme value is 28, that is of 64 QAM. So number of antennas one I'm selecting, and the PDCCS symbol also I'm taking as one symbol. So if you click on calculate, so it will calculate and tell the value of what is the transport block size, what is the code rate, and what is the modulation scheme. Able to see this? I don't know whether it is visible or not. Yes, the transport block size we are getting is 75,376, and is a coding rate. Since here you are getting in fractions, you just have a look. Then modulation scheme is 64 QAM. Yes, able to see. I don't know whether it is small only. Yes, are you able to see this? Hello, my dear students. Hello. Yes, are you able to see that values, transport block size and other things? Yes, students, are you able to see? I'm asking you people only. It is there in red color. Hello. No, I mean
Yes,
your
sir.
just so you can change. You change the number of resource blocks to 6 only. Okay, and even let me keep the modulation coding and scheme as a 64 QAM only. This one, just if I say calculate, you just see the transport block size is changed. Hope able to see what is the value. Is it possible to read and say?
4392.
Yeah, 4392, right? So like that, even if I say the MCS value, that is modulation and coding scheme value, if I say it is 0, means it will be selecting as QPSK. Okay, so just if I say calculate, see the change, right? So now the transport block size is 152.
152.
Yeah, modulation scheme is QPSK. Is that fine? Able to understand how the transport block size is varying? So that depends on the number of resource blocks and the type of modulation scheme and antenna mapping also. So if I say transport block means number of resource blocks is 100, okay, and the modulation scheme if I select 28, that is 64 QAM, and antenna port if I say 2, let me say calculate. Yeah, just able to see how much it is, 75,376. Is it the same value earlier also? Let me change number of PDCCS symbols is 2. Yeah, so it is that value. Okay, hope got the idea. So for the same 100 resource blocks only, if I select the modulation scheme as QPSK, okay, and if I say one antenna port only, and PDCCH is what? Physical downlink control channel it is, okay. So how many symbols you are using for that PDCCS? That is what the meaning of that. You see what is the change now? What is the transport block size? Though the number of resource blocks I have selected 100, because my modulation scheme is QPSK. Okay, with that the transport block size is 2792. Yes or no? Yes, I'm asking you people only. Is it fine?
Yes, sir.
So this is how you should learn. Hmm? So transport block size depends on the number of resource blocks and type of modulation scheme. Okay. So similarly, you can check for uplink also. So transport block size for uplink is there. If you click on this, I think it will show for that. Okay. So here, see what is the change here? SRS is there. Okay. There is signaling reference signal it is. So number of resource blocks. Let me select 100 only. I think we'll be able to understand the difference. 100, and if I select modulation scheme as 28, okay, just if I say calculate, yeah. So with 100 resource blocks, with see here the type of modulation for uplink, it is 16 QAM only, not 64 QAM. Okay, 16 QAM, and the transport block size is 75,376. Okay, so if I make the number of resource blocks as 6 resource blocks, and type of modulation is QPSK, then see the change. See the transport block size is 152 and modulation is QPSK. Okay, so like this you will be able to get an idea. Even if I select 100 resource blocks and if I say QPSK modulation, then the block size, transport block size will be different. Okay, since modulation scheme is QPSK, so now it is 2792 is the transport block size. Okay, fine. Other things also you can check, since I have not yet thought about this uplink control information over PUSEH and all. So when I teach that, then I think you'll be able to understand that. So that's why I'm not showing that now. Okay, so means here you will get channel bandwidth. So whatever the LTE supports, all those is made here. Okay, that is from 3, 5, 10, 15, 20. I think 1.5 is not given here. Then antenna ports also. What is the reporting mode? Then rank value, RI. Then we will be able to select all these things. It will calculate what is the channel quality index, RI, type of hybrid ARQ and other things. Okay. So we'll just have try to understand. Uh, Otherwise, it becomes difficult. Okay. Is that fine?
Yes, sir.